say we have n equals 7, and our permutation is the one listed below. An easy way to get the representation of sigma as a product of cycles is to of disjoint cycles is to start with the first non-fixed point of the permutation, in which case in this case this point is 1, and see where this is mapped by the permutation. So that's mapped to 4, and then follow where 4 is mapped by our permutation. 4 is there, is mapped to 5, and then 5 gets mapped back to 1. So we have this cycle 1, 4, 5 inside our permutation. And did we exhaust all the elements in the set 1 to 7? No, there are still others that we haven't touched. So we can move now to the first element that is not fixed by the remaining part of the permutation, and that would be the element 2. And we proceed in a similar fashion. 2 gets mapped to 6. So we have 2 gets mapped to 6. And then we look where 6 is. 6 is here. 6 gets mapped to 7. 7, we follow 7. 7 gets mapped to 3. And 3 gets mapped to 2. So essentially what we got is that our permutation sigma is a product of the cycle 1, 4, 5 and 2, 6, 7, 3. And this is a product of 2 disjoint cycles, and this is the only way you can write this permutation as a product of 2 disjoint cycles. Again, modulo the order, which means that we can switch the order of the cycles, because the cycle 2, 6, 7, 3 and the cycle 1, 4, 5 are disjoint, and any 2 disjoint cycles commute. And modulo the starting point of each cycle, you have different ways of writing the same cycle 1, 4, 5. As we talked last time, you can write it as 4, 5, 1, or you can write it as 5, 1, 4, and similarly to for the other cycle. Okay, so now let's also mention one fact about cycles. If we have a cycle, let's say A1, A2, AK in Sn, then I claim that if I raise the cycle T to, if I compose it K times, I'm going to get the identity permutation. And this is a pretty straightforward fact. In order to prove it, we just see what this permutation tau composite itself K times, what does it do to every element of the set from 1 to n. So if we look at what tau does to A1, it shifts its index to A2 and so on. It moves A2 to A3 and AK to A1. And then when we look at tau square, at the tau composite tau, basically it shifts A1 first by tau and it becomes A2, and then tau shifts it again, it becomes A3. And so it's not too hard to see that if we do compose tau with itself K times, we're gonna go tau, tau, tau of A1, and the first tau here sends A1 to A2, and the second tau will send A2 to A3, and so on, until you get to the end that it sends A1 back to A1. You go on all these K steps on the cycle A1, A2, all the way back to A1. Now, if you have also an element B that's not on the cycle, that is fixed by the permutation tau, and it's also going to be fixed by any power of tau as well. So just remember this fact that any K cycle, when you raise it to the power K, you get the identity permutation. Now, we can define the following invariant of a permutation, and this is called the order of a permutation. And this is the smallest natural number, K, such that sigma to that permutation, to that power K equals the identity permutation. And before we talk about general permutations, if we look at the previous example where we had a cycle of length K, it's not too hard to see that using extending the previous argument, the order of a cycle of length K is gonna be K. So the order of a cycle of length 2 or of a transposition is gonna be 2. Order of a cycle of length 3 is gonna be 3, and so on. Now, what happens when you have a permutation that's not just a cycle? How can you find its order? How do we know that this parameter, this order of a permutation is actually well defined. Well, this is the way you get to this minimum number k with this property that sigma to the k is identity. Namely, if you take decomposition of a permutation sigma into disjoint cycles, let's just call it tau 1, tau m, and again tau 1 all the way to tau m are pairwise disjoint cycles, then the order of sigma, it's actually the least common multiple of the lengths of the cycles t1, tau 1 all the way to tau m. Like the lengths are actually also the orders of these cycles. So to see why that's the case, well, if we take some natural number r, if we take some natural number r, and we have our decomposition tau 1, tau m, and we raise sigma to the power r, because these cycles tau 1, tau m are disjoint, they commute. And so when we do sigma r, it's going to be this product tau 1, tau m to the power r. But because the cycles commute, then this expression is actually going to equal tau 1 to the r, tau m to the r. And so if we take, this will make it easier to show that if r is actually the least common multiple of the orders or of the lengths of these cycles, it's going to be multiple of each of these lengths. And so tau 1, so if r equals this LCM, then tau 1 to the r is going to be identity, and so on, tau m to the r is going to be identity. So that shows that raising sigma to this power is going to give us identity. So the order of a permutation is well defined. And I leave it as an exercise for you to show that actually this is the smallest power. There's no power smaller than this least common multiple, with the property that sigma to that power is going to be identity. Okay, so that's how you can find the order of a permutation. Now, related to this problem of decomposing a permutation in a product of disjoint cycles is decomposing a permutation or writing a permutation as a product of transpositions, not necessarily disjoint. Now, this is a proposition stated there in red that every permutation in Sn can be written as a product of transposition. So let's just assume n is greater or equal to 2. So the first proof of this result can be done using our previous theorem. Basically, you write sigma as a product of disjoint cycles, and then each cycles, as we've seen in the previous lecture, can be written as a product of transpositions, and then we're done. There's no uniqueness in this proposition at this point. Now, the second proof is a more direct proof and has a bit more intuition into it, and it doesn't use the decomposition into disjoint cycles, and it works as follows. If our permutation is identity, then you can write it as a product of 2 transpositions if you want, or a product of 0 transpositions. Now, if the permutation sigma is not the identity permutation, then you essentially do the thing that your gym teacher used to do when he or she asked you to arrange your class, perhaps in the increasing or order of heights, so or in alphabetical order or in some specified order. And the way that works is you find the first person that is not in the right place, and you move that person to their correct place by switching them with the other person who's occupying the place. So that's a transposition, and you continue this until everybody's put in their own place. So I hope this makes sense. Formally, the way it works is that if you have a permutation that's not identity, then you take a non-fixed point of it, an element A, such that sigma of A is not A. And then let's look at a B. Take B to be the pre-image of A. So if I think about our permutation in the 2-line notation over here on the right, then on the first row, I have A, and corresponding to it, it's some number, some element sigma of A, which is not A. And somewhere else, you have some B, and this is the preimage of A, which is mapped to the position A. And now, what we want to do is we want to switch. So A, instead of being the A here on the second row, instead of being in a position under the A on the first row, is in a wrong position. So we just switch these two places corresponding to A and B. And so formally, this means that we can define this permutation sigma prime, which is sigma multiplied by the transposition AB. And now what does it do? Well, the permutation sigma prime does the same thing as sigma to any element C, which is outside A and B. Okay, that's pretty clear. And then what does sigma prime do to A? Well, our intuition says that it should map A to A. But if you work it out using this formula, you have that sigma prime of A is sigma composed of the transposition AB applied to A. And first thing the transposition does here, it just sends A to B. So we have sigma of B, and we know that sigma of B equals A. And similarly, sigma prime of B is going to equal sigma A. So what happens with sigma prime and sigma? Well, sigma prime fixes more points than sigma, because it fixes everything that sigma fixed before, and it also fixes A, which was not a fixed point for sigma. And so we can continue this procedure until we end up with a permutation that fixes every element. So that's exactly what we do, and we repeat this process. And again, here we're using the fact that we're dealing with permutations of finite set. So this procedure is going to stop. And when it stops, what do we have? We have started with our permutation sigma. We have multiplied to the right by various transpositions, tau 1, let's say up to tau r. And we ended up with the identity permutation epsilon. And therefore, if we get rid of the things on the right-hand side here, then we can see fairly quickly that sigma is going to be this product of transposition tau r minus 1 times tau 1. So you have to be a bit careful here with the order how you make this multiplication. And so this is a product of any permutation as a product of transpositions. So let's see some examples. So let's say n equals 4, and we have this permutation that switches 1 and 2 and 3 with 4. So it's a product of two transpositions. But because 2 times 3 equals 3 times 2, it's the identity. The same product of two transpositions can be written as a product of 4 transpositions. Again, these are the first product had 2 disjoint cycles, 2 disjoint transposition, but the next ones, there, as you can see, they're not disjoint. And you can actually make this into a product of other lengths. So for example, 1, 2, you can write it as 2, 4 times 1, 4 times 2, 4. And 3, 4, you can write it as a product of these 5 transpositions. And you get a product of 8 transpositions. So it's actually not hard to see that any permutation can be written in infinitely many ways as a product of transpositions. So what's the big deal? Well, the big deal is that no matter how you do that, the parity of the number of factors in the product, when you write a permutation as a product of transposition, it will always be the same. So you see here for this permutation, it's a product of 2 transpositions here, it's a product of 4 transpositions here, it's a product of 8 transpositions, it can be written as a product of 6 transpositions, 10, 12, and so on. So this is an important result, which will lead us to define the notion of sign of signature of a permutation. But for now, let's just state it as follows. If we have 2 sets of transposition, let's say sigma 1, sigma k on the left-hand side, and tau 1, tau l on the right-hand side, such that the product of the sigmas equals the product of the taus, then the k and the l must have the same parity. So k must be congruent to l mod 2. And actually, this result is equivalent to the following. If I have a product of transpositions, let's say R transpositions, A1, B1, AR, BR, and their product equals the identity, then R is even. So you can see that the first part implies the second part just by taking all the these things on the right, such that so taking the permutations on the right, the taus, such that their product equals the identity. So then you get the second statement below. But it's actually not hard to see that the statement below also implies the statement above, because if whenever you have this product of sigmas equals the product of taus, you can write this equation in a similar form to what we have here by getting rid of these taus from the right hand side. So the first equation is actually equivalent to the equation where you have the product of the first k permutation and then the other L transpositions. And so if the statement below here is true, then that would imply that k plus L is even, and k plus L is even only if k minus L is even, which is the conclusion that we have there, that k is congruent to L mod 2. Okay, so what we're going to do is we're going to prove this fact here. And all right, so let's move on to do that. Now on the Google Drive, I've placed a file which is related to this topic, and it contains a very nice write-up which is due to Keith Conrad at University of Connecticut, in which he gives various proofs about how the signature of a permutation is defined, and it includes so the proof that I give there is here is adaptive from there, and basically what we're going to prove is that if we have this this product of transpositions A1 B1 A2 B2 AR BR equals the identity, then R must be even. Okay, and now for the proof, we're going to use strong induction on R. And now for the base case, well, the base case, what is it? Can it be R equals 1? Well, it cannot be R equals 1, because if we have a transposition, if I have a transposition A1 B1, then in our notation, when we write A1 B1, we automatically assume that A1 is different from B1. Then the product of a single transposition cannot equal the identity, because the permutation on the left doesn't fix A1 and doesn't fix B1. So there's no way that the product of one transposition is going to be identity. So let's say R equals 2. So that would be our base case. In that case, we have A1 B1 times A2 B2 equals the identity. And what happens? Well, we can multiply to the left, let's say. We can multiply to the left by A1 B1. And so we're going to have A1 B1 times the previous product that was on the left equals A1 B1 on the right. But now these two permutations here give me the identity, because the transposition times itself is the identity, and we end up with A2 B2 equal A1 B1, and basically confirms the obvious fact that the only way you can have a product of two transposition equal the identity is if they're identical, but it can happen. So in that case, R equals 2. And so that that confirms this base case. So this is pretty trivial. Now for the induction step, here's where things are more interesting. So we can assume the statement is true for all products of transpositions with R minus 1 or less factors. So whenever we have R minus 1 or less factors and their product equals the identity, then the number of the factors in that product must be even. And now let's say we have this, our situation, we have this A1, B1, A2, B2, dot, 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 AR, BR equals the identity, okay? Now, here's the thing that we're gonna do here. So we look at first element here in our transposition. Let's say it's A1, and because the result on the right hand side is the identity, we know that in the permutation on the left hand side, A1 must be fixed. Now, the first transposition moves A1 to B1, so it moves it somewhere else. So at some point, maybe A1 travels, various places with these transpositions, but some other transpositions, some other transposition in this product, in the other R-1 factors, must also contain A1 in it. So, okay, so then what we're gonna have? We're gonna have A1, B1, and maybe here somewhere, it could be immediately after, or it could be further away, we have some A1 times BJ equals ARBR equals the identity. And now our job now is to bring a transposition containing A1 to bring it immediately next to this permutation, to this first transposition A1, B1. And to do that, we're gonna use the following facts. Let's say, I will use the notation that Conrad uses in his write-up. A, B, C, D are disjoint letters or numbers. If they're, in that case, the product between A, B, and C, D, it doesn't depend on the order. So these two transpositions commute. So for example, if the transposition immediately to the left of A1 and BJ did not contain any A1 and it did not contain any BJ in it, then by the fact that I wrote here on the right, we could swap the order between them and we move A1 BJ further to the left. Okay. Now, what happens if the permutation to the right, just a second, what happens if the permutation immediately to the right of A1 BJ is not disjoint from A1 BJ? So because I want to bring A1 further all the way to the front, let's just assume that this transposition that I have here, A1 BJ, is the first one that I see when I move to the right after I've seen A1, B1. So it's the first transposition that contains A1. So in this position, we can have we could have some BJ. That's our situation that we're dealing with, and maybe some other element. Let's just call it C. So in that situation, we could have this this type of situation. So then what do we do? Well, how do we swap these things now? So the product that we have there, we can write it as follows. We can write it as BJ times C, BJC, that's a transposition. And if you multiply that by A times B, it turns out that the result is the same thing as AC times BC. So I'll leave it to you to show that the product between these things that I wrote in red are correct. So in that case, what happens is that we can replace this product here, we can replace it by the first permutation that goes to the right is going to be A1C, and the permutation that's going to be here to the first one that goes to the left is going to be A1C, and the one that's going to be to the right is going to be BJC. So let me put the J here as well, BJC. So the same thing as before, we can move, we can replace our product by a different product where the second transposition that contains A1 in this product after the first one is closer and closer to the first position. So you can continue this procedure until we end up with what? Well, we can continue this procedure until we end up with the first transposition that has stayed unchanged, but the second one will be something involving A1. So let's just write it as A1, B2, and then the number of the product, the number of factors has not changed, and we still have R factors on the left. Now, here's what happens next. If B1 equals, so in this situation, we have two cases. If B1 equals B2, then these two permutation transpositions at the beginning, they give us identity. And in that case, we have written our identity permutation on the right as a product of R minus two transposition. And then we can step into our induction hypothesis and conclude that R minus 2 must be even, and therefore R must be even. Okay, so that's the first part. Now let me erase here a little bit. What happens if so if B1 equals B2, then this part is identity, and we use induction, hypothesis, and we get R minus 2. So it's going to imply R minus 2 even, and implies R even. But what if B1 is not equal to B2? Then we're going to have A1, B1, A1, B2, and the rest of them A3, B3, going AR, BR equals the identity. Okay. Then what we do is we rewrite the first part. So the first part can be rewritten, and again, this is not too hard, and I leave it as an exercise for you, as A1, B2 times B2, B1, and you keep the same things for the remaining part, AR, BR, and so on. Okay, and now we start again a similar case as the way we started this this induction step. We have A1, B2 over here, and now this B2 doesn't equal A1, this B1 doesn't equal A1. What have we done in the second product here? We have reduced the number of A1s from the first product, the one that we started with, by 1. And so we can argue that because A1 at the beginning appears in that product, there must be some A1 further down here. So we can go again through the same proof, and we can either end up with a situation that the first two transpositions are the same, in which case again we get R minus 2 equals even, or we can reduce the numbers of A1 furthermore. So eventually you cannot end up with a situation where you have only A1 in the first two transpositions and you don't have it anywhere else, and the product of all these transposition equals the identity, because A1 wouldn't be fixed by the permutation on the left. So eventually you have to end up here, and we get that R minus 2 must be even and R must be even. Okay, so I hope this makes sense. So now, with this thing in mind, we can define the sign or signature of a permutation. And this is as follows. So let's assume, I have a small typo here. Let's assume that our permutation can be, sigma can be written as a product of R transpositions. Then the sign or signature, which will be noted by SGN of sigma, is defined as -1 to the R, let's say mod 2, to 0 if R is even, and to 1 if R is odd. So kind of I'll make it more clear here. Sigma is going to be even if the signature of it is 1, which is the same thing that sigma is a product of even number of transpositions. And the same thing for odd, the sigma is odd, or is the same thing as the signature is -1. And this is the same thing as sigma is a product of odd number of transpositions. Okay. So by our previous results, this is well defined. So a permutation cannot be, essentially the previous proposition stated that a permutation cannot be even and odd at the same time. You cannot write it as a product of an even number of factors of being transpositions and a product in which you have an odd number of factors that are all transpositions. So in particular, the identity is an even permutation. A transposition is an odd permutation. A cycle of length 3 ABC is an even permutation, and you can see fairly easily that because we have this decomposition of a cycle of length k in a product of k-1 transpositions, that a cycle of length k is going to be even if k is odd, and is going to be odd if k is even. So you have to be a bit careful about that. And also an important property of the signature is that if you take two permutations, sigma and tau, and you compose them, the signature of the product equals the product of their signatures. So to spell it out here, if you multiply an even permutation by an even permutation, you get an even permutation. Even times odd and odd times even is odd, and odd times odd is even. So the interesting, I mean, all these facts are interesting, but what happens is that you notice here that when you multiply even permutations by even permutation, you stay even. So if you look at the set of all even permutation in Sn, with the binary operation of function composition, is going to form a group, and it's actually a subgroup of the symmetric group, and this subgroup is called the alternating group An of degree n. And it's not too hard to see that because of this this property here, that we have that the cardinality of Sn, as we know before, it's n factorial, and the cardinality of An is actually n factorial over 2. So we have as many even permutation as you have odd permutation, namely n factorial over 2. Okay. Now, why is this called an the alternating group? It has to do something with the type of polynomial. So let's say we have n variables, x1, x2, xn, and we can look at this multivariate polynomial in this n variables or indeterminants, x1, xn, and this polynomial delta n is the product over all I less than j of xi minus xj. So in the particular case when n equals 2, delta 2 is just one factor, x1 minus x2. When n equals 3, delta 3 is x1 minus x2, x1 minus x3, x2 minus x3. And now we can define for every permutation sigma in Sn, we can define another polynomial, delta n of sigma, which is the product, again, the first part is similar for both of these formulas, is the product over all I less than j. But here, it's not going to be xi minus xj, it's going to be x of sigma I minus x of sigma j. So let's see what happens in this simple case where n equals 3 and the permutation sigma is 1, 2. So if I look at the transposition 1, 2, delta, I guess in this case, it's delta 3 of sigma, it's just going to be x sigma 1 minus x sigma 2 and so on, x sigma 1 minus x sigma 3 times x sigma 2 minus x sigma 3. And when you replace so sigma 1 is 2, sigma 2 is 1, and so on, we get that this equals minus delta n. So delta 3 of sigma equals minus delta n. And so what happens is that for that permutation, so let me write it here, and I'll come back to this definition in a second. for this sigma equals 1, 2, we had that delta 3 sigma equals minus delta 3. And I'll leave it to you as an exercise to take maybe another permutation. Let's take the cycle 1, 2, 3, and to calculate what is delta 3 of tau. And it's not hard to see that this is going to give you delta 3. And actually, one can show that in general, for any n greater or equal to 2, and any sigma in Sn, delta n of sigma is going to equal either delta n or minus delta n. And it's going to be minus delta n if sigma is odd, and delta n if sigma is even. So this polynomial delta n of sigma, you can see it as being obtained from delta n by doing some permutation of its variables or its indeterminants. And such a polynomial whose value changes just by a sign change, so it stays the same or it gets replaced by its negative, when each pair of its variables is permuting, is called an alternating polynomial. And so this delta and sigma is an example of an alternating polynomial. And you know, we have these propositions over here, and you can actually in the textbook for the course, I defined the signature of the polynomial using this using these alternating polynomials. The signature of the permutation using these alternating polynomials, and it's equivalent to what we've done so far. So that's about it about this alternating group and the signature of permutations. Okay. So now let's move off to another topic. Let's count K subsets of n. Again, probably most of you are familiar with this topic. So in the first class, we showed that the number of subsets of a set with n elements is 2 to the n. What if we put a condition on just counting all the K subsets of this set? So let me give you some notation first. So if you have a set S, we sometimes use the notation S choose K is the collection of all K subsets of S. So in particular, if we take S to be our set 1 to n, we can denote this nk as the collection of K subsets of the set n. Okay. And now we can define n choose K, this binomial coefficient, is actually the cardinality of this set. And it's essentially the number of K subsets of n. Okay. And we're going to prove the first proposition here is that, so let's say, let's take 0 less than or equal to K less than or equal to n be two integers. Then we're going to have that n choose K equals n times n minus 1, blah, 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 n minus K plus 1 divided by K factorial. And another formula, which is easier maybe to remember, but maybe not so easy to use, is n factorial divided by K factorial times n minus K factorial. Okay. So there are various ways to prove this fact. So let's do one of them. So let's say, so when we count n choose K, we're counting subsets. So the order doesn't matter. So in n choose K, the order in which our elements are listed does not matter. But let's say I'm going to come up with another another parameter, let's say n and k. Let's say define this parameter as the number of k ordered it's not quite the right name, subsets of n, k ordered tuples, distinct tuples of n. So let's just give some examples, maybe on the second page, on the next page. So let's say 4 choose 2. What is this? Well, here we have a set 4, which is 1, 2, 3, 4. And what are the two subsets of it? Well, let's list the ones that contain 1, 1, 2, 1, 3, 1, 4. What are left that contain 2, 2, 3, and 2, 4. And what is left is 3, 4. So this number is 6. What about n42? So n42, here we're counting ordered pairs. So when we're counting order pairs, yeah, that sounds very smart. Order matters. So we can have 1, 2, but also 2, 1 is different from 1, 2. And then similarly, you can have 1, 3, and you have 3, 1, and so on. 1, 4, 4, 1. And I'll leave it to you to figure out all of them. Essentially, n42, we have two positions. And how many ways? It's kind of similar to counting the number of permutations. How many choices do we have for the number in the first position? You have 4 choices. So four choices there. And once we put one element there, then we cannot use it on the second position. And so we're going to have, on the second position, we're going to have 3 choices. So you get 4 times 3, I'm sorry, on the second position, so it's 12. So in general, it's not, the same argument is going to happen for n and k. If you have, we have k positions. In the first position, we have n choices. In the second position, you have n minus 1. And so just be careful what happens in the last position. So when you get to the last position, this is the kth position. So it means that we have used the k minus 1 elements already. So the number of choices that we have here is n minus k minus 1. The k minus 1 elements that we have used in the first k minus 1 positions. So this number is going to be n times n minus 1 times n minus k plus 1. Okay. So that's how many ordered k tuples you have. But whenever we have an ordered k tuple, or several ordered k tuples correspond to the same subset. So for example, above 1, 2, and 2, 1, they're just a permutation of 1, 2, 1, 3, and 3, 1, they're just permutation of 1, 3, and so on. So with that in mind, we can write that the number of order k tuples, this parameter which we just proved equals, and this kind of falling factorial. What is this going to be? Well, it's going to be the number of all k subsets. And for each k subset, we can permute it. We can have k factorial possible orderings in which they can appear in this parameter n and k. So you have this value. So using this, this fact, we get that n choose k equals this falling factorial divided by k factorial. And yeah, it's essentially an example of a double counting. We counted the same thing in 2 different ways. And so another way that this can be done, so, and I'll do this and then I'll stop. Page 11. this is done in the book. You can show that k times n choose k equals n times n minus 1 choose k minus 1. So, okay, so what's the big deal of this? Well, the way you can prove this fact is by counting in all order pairs of x and a, or where x is an element of our set, a is a subset of our set, cardinality of a is k, and x is an element of a. So you can count the number of ways of forming k teams with a, let's say, designated captain for that team. So you can count this in two ways. If we counted using, let's say, start with the first position, x, well, x is an element of n. So if I look at my set here, let's say this is the set n, and you have 1, 2, blah, 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 all the elements here, n, then x comes from the set. So it means that there are n choices for x. And now once x is chosen, so let's say x is here, I need to choose A, which is a set of k elements that contains x. So if I look at A minus x is a subset of the set n minus x. So it's a subset of a set with n minus 1 element, and cardinality of A minus x is k minus 1. So the number of choices for the remaining elements of the set A is going to be n minus 1 choose k minus 1. And now that's one formula for this number. So we get n times n minus 1 choose k minus 1. Another formula is count the a's first. So how many subsets a's can I pick? Well, there are definitely n choose k such subsets. So that's how many teams I can make. And once I have a team A, how many captains of that team can I find? Well, there are k choices for the element x, because x has to be one element of A. And so you get this formula. And how does it lead to the same result, the same formula as before? Because you can write it, the formula above, you can write it as n choose k equals n over k times n minus 1 choose k minus 1. And then you can repeat. This is n choose k times n minus 1 choose k minus 1 times n minus 2 choose k minus 2. And you do this until this number here becomes 0, and at which point this is going to be, or 0 or 1, in which point you know exactly what your binomial coefficient is going to be, and you end up with the same thing, n minus 1, n minus k plus 1 divided by k factorial. All right, so I'll stop here. Next time we'll talk about binomial formulas, and we're going to start talking about formal power series and generating functions. Thank you very much.